Well, thank you, everybody. Welcome to this evening's lecture meeting hosted by Orwell Astronomical Society. We also welcome members of our neighbouring astronomical societies, Dash Astro, Lyra, Breckland, Athenaeum and North Essex. This evening's speaker is Dame Jocelyn Bell Burnell. Jocelyn was born in Lurgan, Northern Ireland. She attended the Quaker Mount School in York, where she impressed her physics teacher and went on to graduate from Glasgow University in 1965 with a BSc in Natural Philosophy. Jocelyn then moved on to Cambridge University, where she worked to construct the interplanetary scintillation array to study quasars. In 1967, while at Cambridge, she famously discovered pulsars, which were identified as rapidly rotating neutron stars. In recognition of this discovery, Jocelyn's supervisor was awarded the Nobel Prize for Physics. After obtaining a PhD at Cambridge in 1969, Jocelyn has worked at many locations around the world. Her list of honours and awards is extensive. She was appointed CBE for services to astronomy in 1999 and promoted to a Dame Commander of the Order of the British Empire in 2007. Recent awards include the Gold Medal of the Royal Astronomical Society and the Royal Society's Copley Medal. So it gives me great pleasure to introduce this evening's speaker, Professor Dame Jocelyn Bell Burnell. Jocelyn.
Thank you very much. Let's see if we can get my screen up now. Right, are you seeing something full screen?
Yes, that's fine.
Excellent, thank you very much indeed. So, you may well be familiar with the Hubble Deep Field. Hubble stared at this one particular spot in the sky for 143 hours. It's quite a small area. It's said to be less than that covered by a tennis ball when it's 100 meters away. But because they stared for a very long time, they stared very deep into the universe. They picked up very faint things. And this has become a really famous image. And there's some interesting things in it. For example, there still is black between the galaxies. Almost everything in this image is a galaxy. Where's my cursor? Yep. Can you see a cursor?
Yes, we can. Yeah.
Yes, you can. Good. So that's a star. We know it's a star because of the cross shape through the image, the cross being produced in the telescope. I think there's another star somewhere in the field. I can't find it at the moment. Everything else is a galaxy. But one of the disadvantages of staring for 143 hours is if something flares up and dies, you're not able to follow the flare. You get some kind of average over the whole 143 hours. And equally, if something moves, you get a sausage-shaped image, but you don't really know exactly what's going on there because you've averaged over 143 hours. And one of the recent developments in astronomy is studying what we call the transient sky, where we're watching for things that change. That very small area that Hubble stared at does seem to be a very typical area, so it was well chosen, and it gives lots of very interesting results. But as I said, you miss anything that flares or changes its brightness, and you move, or it's hard to recognize anything that moves because it comes out as a blur, a sort of cigar-shaped blur. It's a bit like photographing traffic lights, albeit with a long exposure. A long exposure gives you all the lights half on, but if you want to see the pattern of the lights, you need a series of short exposures. And one of the recent developments in astronomy is that we've started taking short exposures. We've now got the equipment, which means we don't have to expose for hours and hours and hours. We've got much better equipment, and we can take many quick, short pictures, a bit like a movie. And I want to talk about some of the things we found when we look at the sky that way. I'm going to start in the optical, and a number of older telescopes have been repurposed to monitor the night sky, to look for things that are flaring or dimming, or in some instances moving. So Pan-STARRS, for instance, is a telescope in Hawaii, and they got money for it by saying they would look out for killer asteroids, things that were coming to hit the Earth. And they do look out for killer asteroids, but of course they're watching the night sky anyway, and they see lots of things that change their brightness, that flare or maybe dim. I go to the top right next. This is in Australia. This is a Schmidt telescope that's owned by Uppsala University in Sweden. And it also is on the lookout for things that change brightness. But the one that's making the running is on Mount Palomar, the famous Mount Palomar. And what they've done there is they have repurposed a Schmidt telescope there so that it can take rapid exposures. For example, 4 30-second exposures, 10 minutes apart. This they can do because they're not reliant on film, it's digital readout into a computer. And that can be quite a lot quicker. These two images show you the kind of thing that they're finding, although this was actually not done with the Zwicky telescope. The two images there on the right-hand side cover the same part of the sky, albeit with slightly different exposures, but also different dates. The left-hand one is done over the year end, and the right-hand one is done in May 2006. And an object at the center of that blue cross has clearly brightened up. This was actually seen by Hubble, but Hubble was not terribly well designed for this kind of observation. Because what you're typically doing is you're going to take 30-second exposures, and you'll wait 10 minutes, you go do another 30-second exposure, and wait 10 minutes and go do another 30 seconds exposure. And then having done a number of those, you'll probably move away and you'll come back to that patch of sky 28 days later. Now, I'm sure there's a number of amateur optical astronomers amongst you. You'll realize the significance of 28 days. It's the phase of the moon. You come back at the same phase of the moon to this patch of sky. So you've got the same level of background light. And again, you might do your 4 30-second exposures 10 minutes apart. If you do see something's changed, you want to be able to announce it very quickly so that people with other telescopes can say, hey, something's happening to such and such. We better go quick and take a look and swing their telescope. One of the early ones that did really good work was called the Catalina Real-Time Transient Survey. There's actually 2 telescopes in Arizona, one with a 1.5 meter aperture and one with a 0.7 meter aperture. And between them, they could see about 3/4 of the full sky. And it's probably still running, but they started in 2004. And they found something like 12,000 optical objects that change their brightness, 12,000 optical transients. The most common things are active galactic nuclei. Some galaxies have got black holes in their centers, and these can be quite active and pull stuff in on them. Supernovae is exploding stars is another good example. Variables. And this is a map of the whole sky showing the Catalina events. The Milky Way is along the center, and they didn't try doing observations there because it was too crowded. The red dots are supernovae, exploding stars. The blue dots are cataclysmic variables. The green are external galaxies with active nuclei. And magenta is everything else. And you can probably see this kind of pattern. It's not random. Apart from that kind of pattern, it's random. But this is the ecliptic plane. This is the plane that the sun and the planets move in. And they're clearly picking up a number of, well, they've probably eliminated major planets, but they've probably got a lot of minor planets. And they move, so they get picked up. So this has become quite big business now. Catalina is one of the old ones and is probably no longer making the running. I think the one that's making the running at the moment is Palomar, Mount Palomar. They've taken an old camera and rejigged it so as it can take lots of short exposures. And they've been running here since 2008. And as well as finding lots of more supernovae and different supernovae, it's also been finding all sorts of new things, different things. And it's making very short exposures, seeing things that explode, seeing things that disappear. Another interesting development, this actually came from New Zealand, from MOA. Forgotten what MOA stands for, as well as being a Southern Hemisphere animal extinct. You're at a telescope and you're interested in things that change their brightness. So you're looking out for things that change your brightness. And here on the first frame, you see something that changes its brightness. You're observing this star. But what's happened is that another star has come between you and it. And it's given this change in total brightness, which initially you think might be due to this yellow star that you're observing. But you probably can work out quite quickly that another star has come between you and your pet yellow star. Suppose this other star has a planet. Then what you will see is this for the red star, followed a bit later by the blip of the planet. Sorry, my computer is determined to move on. Don't have proper control of it. Now, sometimes they've seen the blip of the main star, and then quite a bit later, a blip from something else. And it's the planet that's further away from its parent star. All that is fairly understandable, but occasionally they see the planetary blip and no red star, no parent star. That's a free floating planet, an orphan planet. And this telescope in New Zealand was the first to find these. We now know of thousands of these free floating planets. It seems to be there are quite a lot of planets milling around that are no longer attached to a star. Now, so far, I've been talking about what optical astronomers have been finding. I've been looking at this tiny bit of the whole spectrum. It stretches from radio waves through millimeter and infrared to the light that we can see, through ultraviolet to X-rays and to gamma rays. And we now do transient astronomy across the whole of this spectrum. So I'm going to go first to gamma rays, which are really energetic little bombs landing, if you like. You will have come across gamma rays. They're sometimes used for cancer radiation treatment. They're also used for the sterilization of equipment in hospitals. But astronomers have started finding gamma rays as well. So I'm going to say a little bit about transient gamma ray events. And there's an interesting backstory here. We're going back to the 1960s, and the USA and the USSR had signed a test ban treaty agreeing not to do atmospheric tests of nuclear weapons or tests of nuclear weapons in the atmosphere. The United States didn't trust the Soviets, so they put up a number of satellites to check, because if the Soviets did test a weapon or whatever in the Earth's atmosphere, there'd be a burst of gamma rays along with the test. The test would produce a spurt of gamma rays. So they put up satellites, and this is a picture of one of them. It's a mock-up, but that's what it looked like. This is way back about 1967, so it's a pretty primitive satellite. So they had simple satellites to look for gamma ray bursts coming up from the Earth's atmosphere, probably above the USSR. But to make sure, they actually had 3 such satellites up at any one time so that they could get a fix on where this burst of gamma rays was coming from. They were called the Vela satellites, and they found some bursts. Starting in 1967. The curious thing was the bursts weren't coming up from the atmosphere over the USSR. They weren't coming up from the atmosphere at all. They were actually coming down from outer space. This is a rather later observation of one such burst. Gamma ray burst 1997, December 14. And it's actually done in the X-ray band rather than gamma ray. But you see, it's all fairly quiet, chuntering along gently, and then wham! And this actually looks like a double burst. And it lasts about 20 seconds and shuts up, and it all goes quiet again. Now, something that lasts about 20 seconds, and you've no idea where it's coming from, is quite hard to prepare for. And they had quite a lot of trouble actually getting enough information on these things to work out what they were and where they were coming from. But they fairly quickly became convinced they were coming from the sky. And by 1973, they were allowed to publish the information about these bursts. And lots of people started looking at them with their satellites or their balloons. And there was a big puzzle. What are they? What's producing them? Where are they coming from? By the time we had over 2,000, almost 3,000 of them from a satellite called BATSI, you could plot their position on the sky. And this has got the sky, oh dear, sorry, my computer is being real trouble tonight. They've opened up the sky. This is the galactic plane, the Milky Way along here. And that's North Milky Way pole, North Galactic pole, and South Galactic pole. And the different colors show the different kinds of intensities. And they seem to be coming evenly from all over. Now, if something comes evenly from all over, they're not showing any sign of clustering to the plane of the galaxy, to the Milky Way. So they're either extremely close, so they're not clustered to the plane of the Milky Way, or they're extremely distant. They're from away beyond our galaxy, so they're nothing to do with our galaxy, so they're not clustered to the Milky Way. And the argument about whether they were very near or very far raged for quite a long time. They're typically picking up about one a day, and while it was on, it was the brightest thing in the gamma ray sky. by quite a margin. They continued to collect data on these, and they made a plot of the number against how long the burst lasts. And you actually get a double humped distribution with the break at about 2 seconds. So actually they've discovered two different things in one. So you've got one group of gamma ray bursts, which are typically about half a second long, and another group of gamma ray bursts that might be 50 seconds long. We now believe that the short ones are what happens when two neutron stars merge to make a supermassive neutron star or something even more exotic. I'll talk about the long ones a bit later, but there's been recent evidence tying up this definition, and I'll talk a bit more about it in a little bit. The short gamma ray bursts, two neutron stars merging. Here's two neutron stars orbiting each other. They gradually get closer, they merge. We now know there's a gravitational wave comes out of this merger, and there's also some jets. And if the jets are lined up on us, we get a good strong signal. The long gamma ray bursts, we now believe are due to an extra big supernova, a hypernova. A high mass star like a red giant collapses. Here it is collapsing. It collapses right down to make a black hole or a quark or maybe a neutron star. It becomes so dense that it expels a lot of its outer layers in a super big explosion. And it also produces a very narrow burst of jet of gamma rays. It turns out that the long bursts come from distant galaxies, really distant galaxies. And these two photographs were what clinched it. January the 23rd, there was 1999, there was an announcement of a gamma ray burst. Optical astronomers got taking pictures quickly. And this was one on the right, was one of the pictures taken. And at the tip of the arrow, you can see that there is an object. The left-hand photograph, taken with a different telescope actually, same field of view, you can see it's got the same bright stars. At the tip of the arrow in the left-hand image, there's nothing very much. It was ascertained that the thing at the tip of the arrow in the right-hand frame was a galaxy, a distant galaxy. For something to be so bright in a distant galaxy, it must be very, very bright. Or else maybe it has a very, very narrowly focused beam, a bit like a laser beam, you know, really, really narrow, and all the energy put into that narrow beam. We now believe that we have a few of these explosions per galaxy per million years. Moving on to another kind of event, things called tidal disruption events. So here in the image, we have a black hole. Up top left, we have a star, which is on a track that's taking us perilously close to the black hole. As the star moves, where's the cursor gone? Oops. Sorry, there we go. As the star moves on its track towards the black hole, it first of all gets pulled out into a cigar shape because there's stronger gravity this end than that end. And as the star moves even closer to the black hole, it begins to break up. The cigar fragments into lots and lots of bits. And the bits fall into the black hole, one after the other. And this gives us a string of gamma rays or X-rays or radio flares from close to a black hole. we are now finding a lot of these, and they're becoming studied quite a lot, and they've got some very interesting phenomena. For example, there's a curious fundamental particle called a neutrino, and it now seems that neutrinos get emitted in these tidal disruption events. That must be from very close to the black hole. Neutrinos don't interact with much, so they travel quite well from the black hole to us. There's also some ultra-long gamma ray bursts. The SWIFT satellite, which was an X-ray astronomy satellite with some gamma rays, it found a 2-day gamma ray burst. Never seen anything like it before. It may be a tidal disruption event like I was just talking about, and maybe some more have been found. This is the Crab Nebula, M1, the remnants of the star that exploded in 1065 AD and with a pulsar in the center. The satellites Fermi and Agile, which are gamma ray satellites, have found enormous flares, 30-fold increases in the gamma ray flux from the Crab Nebula. It's probably something to do with the pulsar, but they haven't been able to position it that accurately. The flares last several days, so it's very unclear what we're dealing with, but interesting stuff again. When you start looking for things that flash and pop and bang, you start finding them, and you find more than you expect, and you find a greater diversity than you expect. So I'm now going to talk a bit about transients seen by radio astronomers, transients at radio wavelengths. And I will have to talk to you about dispersion of radio waves, but I'll start by talking about the dispersion of light. So you may all have seen this. Here's a prism. Here's a ray of white light coming shining on the prism, and it gets split. The white light gets split into its constituent colors, red, orange, yellow. Same thing happens in a rainbow. I'm sure you've seen that as well. And that's called dispersion, when the different wavelengths, different frequencies get spread out. Something similar can happen with radio waves. Radio waves can be spread out into their constituent frequencies or constituent wavelengths. This was first discovered by people who listen to the sort of tweaks and flicks and bangs and hums that come from the near Earth environment. If there's a lightning strike on the other side of the Earth, it produces a sharp burst of radio waves. Those radio waves will travel around following the big loop of the magnetic field and come down again to Earth and can get picked up by radio amateurs. But because as the radio wave travels on this big loop, it's passing some free electrons, higher frequencies will travel faster than lower ones, and so the radio amateur hears a whistle. And let's see if I can get this to work. I forgot to check it. You hear the whistle, which we would represent by this kind of line, starting at a high frequency, going down and down and down and down and down. And that spread out, stretch out, is caused by free electrons. This particular graph has two other radio bursts that are produced locally. So there's one here. And you see, it's not spread out in a curve like this. All the frequencies from 2560 hertz down to 640 hertz, all the frequencies arrive at the same time. So that comes in as a sort of, and there's another double one here. So radio waves that have traveled little or no distance give a single sort of, and things that have traveled a distance give this descending whistle. And it's called a whistler. Now, that whistling is caused by electrons in the near Earth environment, within the area where the Earth's magnetic field works. Turning now to pulsars, which we now believe are very, very compact stars weighing something like the sun, but only 10 kilometers radius, so incredibly tightly packed. Spinning very, very fast, with a magnetic field that is offset from the spin axis. Where's my cursor gone? Yeah. Oh dear. What the heck? Wait, I've lost control of my what am I going to do? I'm pressing it. Oh, sorry. Right. So this will let me go back. And so, here. Right. So the pulsar has a very strong magnetic field that's inclined to the spin axis. And this very strong magnetic field appears to produce quite a narrow beam of radio waves. So you can think of this as a trumpet out of which comes a beam of radio waves, and there's another one going in the opposite direction. And as the star spins, this beam of radio waves cones around the sky. And if it falls on the Earth, we see a pulse each time it falls on the Earth. Now, the radio signal that comes out of this is quite broadband, but as it travels through space, there are free electrons. And when we pick it up on Earth, the high frequencies arrive before the low frequencies. So if you listen to it, it would give some kind of whistle, like the whistler that you listened to a minute or two ago. Pulsar astronomers always make that kind of plot because one of the hazards is locally produced radio signals, badly suppressed cars, aircraft altimeters, pirate radio stations. So radio astronomers always make a plot of frequency against time and look for that sweep down like you saw in the terrestrial signal. How fast the signal sweeps down depends on how many electrons it's come past. No electrons means very little sweep. A big slow sweep means lots of electrons and therefore a distant pulsar. So one day some pulsar astronomers picked up this particular pulse, and you can see, okay, a bit of noise, and then wham, there's a short pulse, and then it's gone again. And if they make this what they call waterfall plot of frequency against time, you can see that it's got a nice, slow, slightly curved descending thing. It's coming from some distance. It's not local. It's not interference. The snag is when you work out from the slope of this curve how far away it is, you realize that it's way beyond our galaxy. And all the pulsars we know so far are in our galaxy or in the Magellanic Clouds, which are our very near neighbors. This is very, very distant. And there was only one pulse from the thing, whatever it was. So was it real? It looks, this curve plot looks lovely. It looks perfect. But for a long time, they weren't too sure whether or not they should publish. They finally did. Because there was still nothing like it ever seen again, people weren't quite sure whether to believe it or not. But it turns out that they had discovered the first of a whole new phenomenon called fast radio bursts. So now astronomers are picking up fast radio bursts, one a day, several a day maybe. We now know of over 1,000 different sources of these fast radio bursts. There's not usually anything other than the radio signal, so it's a bit hard to know what we're dealing with. So the bursts are short. Oh, that's out of date, that figure, 7 or 18. So here's some examples of other bursts. And by studying the sweep down of the signal, you can get an estimate of the distance, and they're way beyond the galaxy. Redshifts 0.5 to 1 is the most common one. There was an interesting episode in Australia at the Parkes Radio Telescope, where they found not only these kinds of bursts, but a slightly different kind of burst, which they couldn't make sense of until a graduate student made a plot of what time of day these funny bursts appeared at. And they tended to appear between 12 noon and 1 p.m. What do we do between 12 noon and 1 p.m? We have lunch. Turns out there was a microwave oven about half a mile away, and it was actually in a building used by the observatory staff, and they had a microwave oven in the staff canteen. And people were heating up their lunch in the microwave oven and then stopping the microwave by opening the door. Take note, folks, if you stop a microwave by opening a door, there is a short burst of microwaves gets out and hits you in the chest before the oven switches off. And that's what these funny Australian bursts were. So remember, press the stop button on your microwave, please. So all sorts of things are happening. All things are, all sorts of theories are around, and some people, some of the slightly madder people maybe, have started wondering about blitzars. Could you get an extra massive neutron star, pulsar body, maybe formed in some special circumstances? While it's rotating rapidly, it's doing okay, but as its rotation gradually slows, and then it's more likely to collapse to a black hole, and that might give a burst. Could that explain these funny radio bursts? It's a nice idea. It's not an idea that's universally accepted yet, but then we haven't got a good explanation yet for what these are. So, you know, sensible ideas and off-the-wall ideas are all around at the moment. This being, I think, one of the slightly more off-the-wall ones, but we'll see. There are many new telescopes coming along, and this, I think, is one of the most exciting ones, except that start of observing has actually been delayed till about 2022. This used to be known as the Large Synoptic Survey Telescope. It's now being named the Vera Rubin Telescope, the first telescope, big telescope to be named after a woman. It's got an 8.4 meter diameter mirror. There's a person to scale. There's another person. It's being built in Chile, and its whole purpose is to look for things that flare in the night. And these figures vary. There'll be at least 1 million alerts per night, maybe 10 million per night. And you're going to have to do computer filtering of these things. The whole thing's going to have to be the whole data analysis has got to be done by computers, and it's quite a high data rate. So it's a very interesting development. COVID has delayed it a bit, so it's probably later this year that it starts observing. And it's going to be very interesting to see what kinds of alerts it picks up. The data analysis system will not only do the data analysis, but when it's found something that the data analysis, thinks is a viable transient, it will automatically send a message, an email, to all the other telescopes around the world, so that if they wish, they can interrupt their regular observing program and go and look at this funny thing flaring. So watch this space. This is going to be very, very exciting, and probably quite overwhelming as well. There are new radio telescopes being built. The major one being built at the moment is called the Square Kilometre Array. Part of it's in South Africa and part of it's in Australia. And it'll be made up of many, many dishes, but all the dish areas added up together will come to a square kilometre. And transient detection, detecting things that flare, is one of its key projects. Indeed, there are some bits of this telescope that already exist. This is part of the Australian, well, one of the bits of one of the Australian telescopes. The previous slide was the South African one. And between Australia, near Perth, and South Africa, we're going to have some fantastic new radio telescopes coming along. And even their precursors are producing amazing data. You know, they're only a subset of the whole, but they're already making a big, big difference to the field. There's also been a low frequency array developed in recent years. Its main hub is in the Netherlands, but there are outstations in Germany and Sweden and France, and one, it's Chilbolton, Hampshire. That's called LOFAR, the low frequency array. And it too will be able to provide data on transients, I expect. So LOFAR doesn't look much like any existing radio telescopes. The low frequency ones are these funny tripods, quadrupods. And the high frequency bit, well, it's all under the black polythene. You could use LOFAR with lots and lots of different beams. So you could have lots of pulsars being observed at the same time, or lots of quasars being observed at the same time with these multiple beams. But LOFAR also has transients, things that vary, as one of its key projects. I don't think they've found any at low frequencies yet, or maybe just one. Not quite sure why, but we'll need more information, more data to be really sure. So transient astronomy is a branch of astronomy that I think is just coming of age. I think it's going to be dominating in the next couple of decades. And I think fasten your seatbelts, because anything could happen. I think it's going to be very exciting and very interesting. So watch this space. And thank you for your interest. Thank you for your attention.
Well, thank you very much, Jocelyn. That was fantastic. If anyone has any question, I've now enabled the chat facility. So if you'd like to type your questions in, so we'll give a few minutes.
Can I ask a question, John Barbrook?
Mm-hmm.
Go on, John.
8 years ago, amongst other things, I was fitted with a pacemaker.
Right.
And when they fitted the pacemaker, they warned me to watch out for induction hobs.
Yes.
And microwave ovens.
Uh-huh.
And iPhones. So I questioned the iPhone. They said, well, because the chances are you'll put this in your shirt pocket and this will be right over the top of your pacemaker. So yes. Beware. So there we are. That's my first introduction.
Very interesting. Okay. Well, I hope none of these bursts will upset the pacemaker. I don't think that's strong. I think you'd need a much bigger collecting area to feel the effects.
So we haven't actually got any questions yet in the chat facility. So just a reminder, if you'd like to enter a question. Yes, we have one. So which types of telescope are used to search for type 1 supernovae? Very dim, very redshifted type.
Yeah, optical infrared mainly. That's supernovae mostly done with optical telescopes.
And you mentioned that long gamma ray bursts are only from very distant galaxies. Why is that? Yeah. $10 million question.
Yeah, I wish we knew. Obviously, there are more distant galaxies than there are nearby galaxies. So that's probably why it's distant galaxies will pick them up. But it is striking that you can pick them up from distant galaxies. You'd expect them to be faint.
So we have, thank you for a fascinating talk. What additional exotic transient phenomena do you think may be discovered in years to come? Or do you hope we will, or do you hope will be discovered? Yeah.
Yeah, I'm actually very amazed by all the things that have already been discovered. And I'm not sure I've got the flexibility of brain power to imagine other things. There's another whole branch of astronomy that's just opening up called gravitational radiation, which is finding particularly black holes merging with black holes, which we didn't expect. Sometimes neutron stars merging with black holes, or neutron stars merging with neutron stars. And in fact, they're finding black holes of a mass that we didn't know existed. So I think the best place to look out for really unexpected things is with gravitational wave telescopes, which are a whole new ball game that I haven't talked about, but that's where I think the action's going to be in the fairly near future.
LIGO and the like, yeah.
That's right, LIGO and Virgo and yeah.
All right, question, are magnetars the same as blitzars?
Blitzars are an idea in somebody's head. Magnetars are known to exist. Whether magnetars are really different from pulsars or just one end of the distribution is being debated. It's a bit unclear still, to be honest. And there's another phenomenon around the fast radio bursts that how do they relate to magnetars and how do they, So yeah, as always in research in new topics, a lot is unclear at the moment.
Yeah. Right, will the James Webb telescope in infrared spectrum observe transients?
I'm not sure. To observe transients, you have to have very good time resolution. And I'm not quite sure what integration time options there are on the James Webb. It was designed long before short duration events came our way, before we became aware of them. So it may only have long integration times. I'm not sure. I should look into that, but I don't know at the moment. I'd be delighted if it has short integration times.
Thank you. Any more questions on chat? We've reached the end at the moment. So has anybody got a live question they'd like to ask?
Nobody else will, can I?
Please.
Yeah, sorry, can I go back to the type 1A supernova again? I probably wasn't very correct with my question. What I was really thinking was, how do you go about searching for things that are that dim? You need a sort of big telescope looking for a long while. yeah, a lot of the transient stuff seems to be done with, you know, quick, short exposures.
Yes.
You're not going to get the depth of, sorry, Karen.
Yeah, you're right. But because the technology's got a lot better, the detectors have got a lot better. A 40-centimeter telescope will pick up quite a lot of supernovae, for example. So because we're making better use of the light that comes our way, put it that way, we're seeing more things, and we're seeing transient things amongst the more things we see. So
Okay.
the old Palomar telescope, for instance, that's now used as part of the Zwicky telescope, fantastic. Actually, it's not the old Palomar, it's the old Schmidt. And Schmidts are only 50 centimeters, 80 centimeter mirrors, something like that. But with a good piece of kit on the back of it, it's surprising what you can do.
Thanks.
Anybody else?
Yeah, anybody else? You can unmute yourself if you'd like to ask a question.
Well, looks though you've explained everything to everybody's satisfaction, Jocelyn. So thank you very much once again.
Thank you. My pleasure. Thank you. Take care, everybody. Keep safe.
Thank you very much, Jocelyn.
Yeah, thank you. Bye now.
Thank you.